Hello, statistics students. I hope you are all doing well. Welcome back to you. In today's lesson, we are going to basically review a little bit. We've done two things recently. We have transformed random variables, and we have combined random variables. Now, they seem kind of similar sometimes, and so today I want to do them side by side so we can kind of see the difference, so we can see the different modifications they make to each distribution. So that way you know, wait, do I add the standard deviations? Do I multiply this? Do I add this? How do I get the means? They have some pretty easy rules, but because they're easy, it's easy to get them mixed up. And so we're going to do them side by side so we can see them both in action and see kind of the nuances and the differences between them. You do have a homework assignment on sapling there waiting for you, but you'll have time in class to get that going. I don't have a ton here for you today. And then we are going to be trying to have quiz 4 on Wednesday. All right, so here's our first scenario. A pet store is selling hamsters. Suppose a random hamster's weight can be modeled by a normal model with a mean of 5 and a standard deviation of 1.2. So let's call this random variable a name, all right? We'll give it x. So x is equal to the weight of a hamster. And so we know the shape is normal. We know the average of x is 5. And we know the standard deviation of x is 1.2. All right, so now we're going to do some things to this distribution, this random variable x. So suppose you buy a hamster and it comes in a box that weighs 2 ounces. Describe the distribution for t, the total weight of hamster plus box. I think I had this one on the Desmos for you, and so hopefully this looks familiar, but if not, this is a transformation. All right, we're just taking x and we're transforming it a little bit. So t, my random variable t now, is equal to, well, it's 1 hamster plus the 2 ounces of the box. And the box is always going to be 2 ounces, so it's a constant. It'll be x plus 2. All right, so what does that change? Well, the shape, well, that doesn't change the shape, so our shape is still going to be normal. Does that change the average? Yes, it does. All right, so our new average of this variable t is equal to 5 plus 2. The average goes up by 2, so our new average will be 7 ounces. Does it change the standard deviation? No. No, it doesn't, because we're just adding 2 to everything. The whole curve is sliding over. It's not becoming more spread out. So the standard deviation of t, because we're just doing addition, does not change. So it's still going to be 1.2. All right. Similar scenario with the same story here. Suppose you buy 4 hamsters, and they all get put into one box. Describe the distribution for T4, the total weight of the box plus 4 hamsters. All right, so T4 is going to equal, all right, well, we have 4 hamsters. That's 4 x's. X plus x plus x plus x. Here are my 4 hamsters. But then they also have one box, plus 2. That is T4. Now you might be thinking, oh, bull, 4 x's. Isn't 4 x's just 4x? And unfortunately, in this case, no. you cannot, I'm going to put this down, but I'm going to erase it, so don't write this with me. This is not equal to 4x plus 2. The algebra does not work that way because here we only have one random hamster. We get to pick one random hamster, and then we make it 4 times as big. I'm not taking one hamster and making it 4 times as big. All right, that's not what's happening. I am taking 4 different hamsters. And so technically these x's are not all the same. So sometimes you will see someone put like a 1 under that one, a 2 under that one, a 3, and a 4, because the first hamster could be heavy. The second hamster could be light. The third hamster could be middle-ish. And the fourth hamster could be something else entirely. Those x's are technically all different, which is why this problem is a combination. All right, we are combining random variables here. But we can't do the algebra combination and turn that into 4x because each of those x's is a different hamster. All right, so what does that do to my shape? Well, the shape is still going to be normal. What's going to happen to my center? The mu of t4. Well, I am going to add up all the averages. This is going to be 5 plus 5 plus 5 plus 5 plus 2. You get to add the averages of all of these random variables and the constant at the end. So we are expecting, all right, an average of 22. Now what about my spread? All right, now here again, we cannot add the standard deviations, but the standard deviations are going to change. The standard deviation is going to be bigger than the 1.2 of what it was. It's going to be bigger than 1.2. 4 random variables are going to be more spread out than 1. So if you remember, this is going to be the square root, and we have to square the standard deviations when we add them. So that'll be 1.2 squared plus 1.2 squared plus 1.2 squared plus 1.2 squared. There are the 4 hamsters and their standard deviations. We cannot simply add the standard deviations. We have to add the variance. I'm not cutting that off, am I? No, I don't think so. We have to add the standard deviations together, but then we have to add the variances together by squaring the standard deviations. That's our formula there. Is equal to, all right, let me type that in. So we've got the square root of 1.2 squared plus 1.2 squared plus 1.2 squared. 1, 2, 3, and one more for all 4 hamsters. So the standard deviation is going to be 2.4. All right, so yes, it did go up. It was 1.2, now it's 2.4. It is bigger, but it is not the sum total. And just an FYI, the plus 2 did not change the standard deviation, did it? All right, that one did not change the standard deviation at all. All right, well, now I can ask you some questions. Now that we have these models completely described, I can ask you some probability questions. So, what is the probability that your hamster and box weigh more than 7.5 ounces? Okay, so this is the single hamster and the one box. What are the chances that it's more than 7.5? All right, let me draw you a picture real quick because it's always good to draw a picture. All right, so the center was 7, and we added 1.2, and we subtracted 1.2 for my standard deviations. And I want to know what is this probability that it's more than 7.5. So 7.5 is somewhere over here, isn't it? Let's call that 7.5. So I want to shade in this right here. And I want to find that area. Well, that's simply a normal CDF. So grab your calculator, second distribution, normal CDF. The lower is 7.5. The upper is infinity because it's going up forever. And then our mean is 7, and the standard deviation is 1.2. And so we get 0.338. All right, so the probability that a hamster, which we called t, right? T was our variable, is greater than or equal to 7.5 is equal to 0.338. So 33.8%. There's a 33.8% chance that our hamster and box will weigh more than 7.5 ounces. All right, now what about for our 4 hamsters in a box? All right, what is the probability, that's over here, that your 4 hamsters in a box weigh less than 18 ounces? All right, so again, we got ourselves a normal model. All right, where's the center? The center is 22. The standard deviation is 2.4. So plus 2.4 over and over and over again, and minus 2.4 over and over again. Let's see, that means 18 will be somewhere over here. I'm not exactly sure where, but 18 is over here somewhere. And what are the chances it is less than 18? All right, so we're coloring in to the left this time. Well, again, a normal CDF. Second distribution, normal CDF. Let's see, lower this time. Well, I'm going to infinity, so that's negative 9999999. Upper is 18. The center is 22. And 2.4 for the standard deviation. So there's a 0.0477. So the probability here, for this time, the probability that t sub 4 is less than 18 is equal to, what was it, 0.0477? I think that rounded up to an 8. So there's a 4.7% chance. All right, let's do one more together here. So again, we're looking at the difference between transforming and combining random variables. This one's about sheep. All right, this one's about sheep. Suppose the weight of a random sheep can be modeled by a normal model with mu sub s of 65 and the standard deviation of 9 pounds. All right, so that's my s. All right, that's my random variable s for sheep. All right, now suppose you are loading 10 sheep onto a trailer for transport. What is the probability that this trailer will be loaded down with more than 680 pounds? All right. All right, let's call this T for a trailer of sheep. We got a trailer of sheep. All right, so what is the shape? Well, if it was normal before, yep, normal, it's normal after. All right, so what are we doing here? Are we transforming a variable or are we combining it? Well, if we have 10 of these sheep, that's going to be s plus s plus s plus s plus s, etc. All right, t is equal to s plus s plus s plus s. All right, 10 of them, right? We're combining random variables. Now, unfortunately, that is not 10s. All right, it has to be S, 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 S. If you want to put a little 1, 2, 3, 4, all the way to S sub 10, that's 10 sheep. So our average, though, is simply 10 of the means, 10 of 65s. So that is just 10 times 65, which is 650 pounds. The standard deviation of t is equal to the square root. All right, and I have to square and add them. So that's 9 squared plus 9 squared plus 9 squared. I have to have 10 of these. All right, in that square root. Now there, if you do want to type it into your calculator a little bit shorter, there, because you do actually have 10 of those, and that is just numbers, you can do 10 times 9 squared. There you can simplify it in that mathematics a little bit for yourself. So let's find those. So square root of 10 times 9 squared, which is 28.46. Now the question, what are the chances that it's going to weigh more than 680 pounds? All right, I am a teacher. I have to draw a picture. All right, there is my normal model. I know the center is 650. I want to know the chances of it being more than 680. 680 is somewhere over here. I color it in. All right, once I have my visual, I can now type this into the calculator to my normal CDF. So the lower is 680. The standard or no, the upper is infinity. The mean is 650. And the standard deviation was 28.46. So there is a 0.1459, so 0.146. The probability that my trailer o' sheep is more than 680 pounds is 0.14, what was it? 6. So a 14.6% chance that the trailer is over 680 pounds with those 10 sheep on it. And now a silly one. We got to end with the silly one here. All right, just so you can see the difference. Mutant sheep. Call that your picture of the day for today. All right, we got a mutant sheep. Mr. Bolt has created a mutant sheep that is 10 times the size of a regular sheep. What is the probability that this sheep weighs more than 680 pounds? All right, so M, my mutant sheep, is equal to 10 sheep. It's 10 times the size. So that will be 10s. But this time I do 10s's because I'm only picking one sheep. And it's 10 times the size. So this one is 10 times s, not s plus s plus s plus s, etc., etc. This one is 10s. So now if I want to find the shape would still be normal. The average of mutant sheep would still be 650 because you're multiplying the mean by 10. But the standard deviation this time would not be the same. If you're multiplying, all right, a single sheep, you do just multiply the standard deviation. So the 9 pounds times 10. All right, that you do multiply the standard deviation with multiplication. This is a silly example, but I'm hoping you can see the difference between this one and the previous. All right, so we got 90 pounds. Now we do our normal model. What are the chances? Let's see, we're at 650. What are the chances this sheep is over 680? But now the standard deviation is 90. So 680 is my lower, infinity is my upper, but now 90 is my standard deviation. And you can see we're much bigger now. Now the chances is 30.369. The probability that my mutant sheep is over 680 is 0.369, or roughly 37%. All right, so hopefully there you can see the difference here between how we calculate the standard deviations. Are you adding multiple random things, or are you multiplying one random thing? Okay, are you looking at many random sheep, or are you multiplying one mutant sheep? That changes how the normal model gets transformed. All right, everybody, that's it for me here. I've got a homework for you on sapling. I think it's actually homework 4 and not homework 5, if I'm not mistaken again. Okay, so try that out. You can get a good early start on that now, and that's due Wednesday along with our quiz. Have a good day, everybody.